This week, we've been looking at solving differential equations. Remember that a differential equation will give us a family of solutions that we call the general solution. If we add in an initial condition or initial conditions, we can narrow this down to a particular member of that family. If you would recall, yesterday we had a differential equation y double prime minus 3y prime minus 4y equals 0. And we guessed what the solution should be. We guessed that the solution should have the form some constant times e to the kt. Then we plugged our guess back into the equation to figure out what values of k would work. The differential equation told us the values of k, told us that the terms should be an e to the minus t and an e to the 4t. But we still had those two arbitrary constants. This is exactly analogous to when we were integrating and we had to write plus c at the end of all of our antiderivatives. The plus c is part of the family of functions. Those constants of integration, those plus c's, are the same as the arbitrary constants that we get in our general solution. If we have some initial condition, we can use those to figure out the constants and get a particular solution. So for example, I'd know that y of 0 is equal to 8. And let's say we also know that y prime of 0 is equal to 7. In this case, I gave you two pieces of information for your initial conditions. I don't know if we want to count this as one initial condition or two initial conditions. It's just one state. We're saying where the function is and how fast it's going. Note that I have two pieces of information in my initial condition. And that makes sense because I'm looking for two arbitrary constants. We need 2 bits of information to find 2 constants. And since we're looking for 2 constants, we need to know 2 things. Just like when we're solving systems of equations, if we want to come down to one solution, if there are 3 variables, we need 3 equations. If there are 4 variables, we would need 4 equations. Unless we're just solving for some relationship between our variables. We're just trying to simplify the description of the relationship between the variables. So let's see how this works. Let's take that first piece of information that y of 0 is equal to 8. That means that if I plug in 0, c1 e to the negative 0 plus c2 e to the 4 times 0, we should come up with 8. So this tells us that C1 plus C2 is equal to 8. Note with this one initial condition, or this one piece of information, the best I can do is find a relationship between C1 and C2. Since we have another piece of information, we can take the derivative of our function. So y prime is going to be minus c1 e to the minus t plus 4c2 e to the 4t. Now, if I plug in 0 into the derivative, we should come up with 7. So minus C1 e to the negative 0 plus 4C2 e to the 4 times 0 equals 7. So now we have another equation, minus C1 plus 4C2 is equal to 7. Now we have two equations and two unknowns. We can come down to one particular solution. So we need to solve this system of equations. If we add them together, we just add the equations together, the C1s cancel out. And 5C2 is equal to 15. So C2 is equal to 3. Since C2 is equal to 3, C1 must be equal to 5. C2 is 3. And so now we've used initial conditions to figure out a particular member of the family from the general solution. Our general solution had two arbitrary constants. One piece of information allowed us to reduce that information to refine our information a little bit more. So if all we knew was y of 0 is equal to 8, we know that C1 plus C2 is equal to 8. So I could call one of the first one C1, and I would know that the other one is 8 minus C1. But simplify the relationship that way and know a little bit more. But to get to a particular solution with no constants, I would need two pieces of information. Any questions? A differential equation plus some initial conditions is called an initial value problem. Note that here we just needed to know two things. In this case, we had initial conditions. What was going on at one particular point? In this case, specifically at 0. All I need to do if I want to find out a C1 and a C2 is to give you two pieces of information. So I can tell you that y of 0 is equal to 8, and I can tell you that y of 1 is equal to some other number. That would just be, that would change what we're looking at. We're looking at a boundary value problem in that case. Big picture here is that the differential equation is defining a family of solutions. If we know something about a particular member of that family, we can figure out a particular member of the family. Any questions? Yeah.
How do you get it?
Since 5C2 is 15, just divide by the 5. Oh, I took C1, the C1's canceled out.
Oh,
C1 minus C1, C2. So
okay.
that's why I picked one of them to be -1, so that I would have to multiply it. This laziness was planned ahead. Does it count as laziness if you plan it 2 days in advance? I think it still does.
No, it's called prepared.
Yeah, we were looking at this system of equations. C1 plus C2 is equal to 8 minus C1 plus 4C2 is equal to 7. Is everybody okay? So if you would recall, this is the very specific thing that we've been working on. Second order, linear, homogeneous, ordinary, differential equations with constant coefficients. What we have to take out of this is a quadratic, well, since it's second order, I can say quadratic. We get a quadratic to be the characteristic polynomial. So we get a polynomial equation for the characteristic equation. Since it's quadratic, it has to have two solutions. And there were three things that could happen. I spelled one wrong. That's not good. So the three things that can happen, we could end up with distinct real zeros. And we write a general solution, C1 e to the K1 times T plus C2 e to the K2 times T. We could also end up with real zeros that are the same. We get a repeated real zero. So we get K and another K. Our characteristic polynomial is a square. We still need to have two linearly independent solutions to make the general solution. So we put C1 e to the KT and C2 times T e to the KT. Now I have linearly independent solutions. I never explained why we definitely need two terms in our general solution for a second order equation. Usually it's enough just to start running around in circles. Now with the second order equation, it's only two terms. Characteristic polynomial has two solutions. And really what's where the discussion happens is x minus 3 squared equals 0 has two solutions. They just both happen to be 3. We count multiplicities. So the quadratic will definitely give us 2. That doesn't explain why we need to. But if I don't mention that last part, I was like, well, see, we get 2. X minus 3 squared has two solutions. They just both have to be 3. And I was like, oh, all right. Then later when you get out of the classroom, you're like, well, hang on a second. That doesn't explain anything. And then you turn around and I'm blocked. That's how it works. I just point that stuff out because I got tired of carrying ninja smoke bombs. You used to have to be like students, be walking out the classroom. Wait a second, that was an inadequate explanation. Then you turn around and I'm like, ha ha ha, too late. I throw a smoke bomb and disappear back to my office. Oh my God, ugh, it's so taxing to like teleport back to my office. I mean, this room is fine. I think I could stretch it into a dimension door, but if I'm like down in some other building, I have to go all the way from 4th level dimension door to 7th level teleport just to not answer a question. You know, it's like, it's a real hassle. I mean, I realize it's been long enough. I have a teleportation circle set up in my office. All I have to do is cast it every day for a year. That first year, I missed one day, totally forgot, had to start the whole process over again. So now I can get away with using a 5th level teleportation circle to get back to my office. But it doesn't come with the smoke bombs like Dimension Door does. So I'm just kidding. I'm not a high level wizard. Is what I'm supposed to tell everybody. I'm just kidding. So when we have a repeated real 0, we can't write e to the kt twice, so we can take the second one 2e to the kt. Usually we'll factor out the e to the kt part and have an e to the kt times a polynomial, c1 plus c2t. We don't want to have to do the product rule any more than we need to. But if you get repeated real 0s, or your characteristic polynomial, this is how you write the general solution. There's a third thing that can happen. When we're solving a quadratic equation, it could be that we end up with complex conjugates. A plus or minus bi. Remember that complex conjugate solutions to complex solutions to polynomial equations with real coefficients will always come in conjugate pairs. They'll always come from some quadratic, and they'll always come in conjugate pairs. Think about the quadratic formula, even though it's trash. Think about the quadratic formula, there's that plus or minus. The negative b plus or minus the square root. And then it's all over 2a. So the negative b over 2a, that's the real part, plus or minus the possible imaginary part with the square root in it. So complex solutions to polynomial equations with real coefficients always come in conjugate pairs. And so we do a different thing to write the general solution. Yesterday, we did the simplest example of this with a pure imaginary solution, x squared plus 1. mostly because we wanted to somehow get sines and cosines to play this game with us. We noticed that if we had, when we had y double prime plus y equals 0, I needed the function y. I needed the second derivative of that function to be like terms. So cosine and sine fit the bill. We didn't do an example where we had complex solutions. If we get pure imaginary, then we'll just have cosine of bt plus sine of bt. If we have complex solutions, the real part shows up just like it does when we had real zeros as solutions. Let's do an example. So if our differential equation is y double prime plus 6y prime plus 13y equals 0, that's going to give us a characteristic polynomial of k squared plus 6k plus 13. This is not factorable over the real numbers. We still need the solutions, or we still need the zeros. So we complete the square. And we get complex solutions. We could also use the quadratic formula for this, but I mean, the quadratic formula is cracked, so we should complete the square. Easy for me to say, I get to pick the problem, so I always just pick a b that's even, because it makes my life easy when I'm completing the square. But if you're like, oh well, what if b is odd, then you have to complete the square. Then it's fraction. And at this point in your mathematical career, you're just not allowed to be afraid of fractions anymore. Well, it's going to be 15 over 7. It's like, oh no, fraction. You don't get to panic at that kind of stuff anymore. You know what I mean? Like if we were little kids in a math class in whatever grade you learned fractions, I don't even know. I feel like I should know that, but I don't. It's fine because fractions will be new and weird. But at this point, they're just other numbers. So we need to build ourselves a general solution. In this case, a is -3, so I'll have e to the -3t. C1 cosine of 2t plus C2 sine of 2t. Now, I just told you that this is how we construct the general solution to this differential equation. You should 100% not just believe me. You're going to, because I'm going to describe what it takes to not just believe me. But we should never just believe someone. You know what I mean? I guess if you're a friend or your partner, you should probably just believe them. But your teachers, you should never just believe them. I'm telling you, never just believe. You know what I mean? Anyone that can't be questioned, anyone in authority that can't be questioned is someone that shouldn't be, first of all, really needs to be questioned. And second of all, shouldn't be in authority. You know what I mean? I'm sure you've had this teacher before in your lifetime. You couldn't challenge them on anything. Not because they set up unchallengeable positions, but because they get mad if you tried it. You know what I mean? I'm especially thinking about high school. You should know, have sympathy for these people. It comes from a place of insecurity. I can stand up here when I'm talking about math, and I can be like, oh, come at me, bro. Because it's math, and I have confidence in my ability to solve the problems. You know what I mean? At least, the very least, start explaining it. A lot of times, teacher, they let their pride get in the way. They think, ooh, I don't want to look bad in front of the class. Like I don't know something, as if they're supposed to know everything. You know what I mean? Happens to parents too. Someday, some of y'all are going to be parents, and your kids are going to ask you questions that you don't have answers to. They're like, well, why does it have to be this way? And you're like, oh, shut up, kid. I'm the parent. Anyway, here's what you need to do. You need to not just take my word for it. It's like, oh, dude, I don't believe that Leach when he says that it's that simple. We're going to have to take the derivative. Derivative of the first times the second. Plus the first times the derivative of the second. Derivative of cosine is negative sine. Derivative of sine is cosine. This is a second order equation. We're going to need the second derivative. Oof. So we're going to want to clean this up because right now it's two product rules, and I'd rather do one product rule, and I see a common term or a common factor of this e to the minus 3t. So that's not going to fit here. So let's keep track of what we have. As far as cosine of 2t goes, I've got minus 3c1 plus 2c2 cosine of 2t. Now I'm really regretting writing this in orange, but I can't change now. It would bother me. But would it bother me more than writing this whole friggin' thing in orange? In the sine of 2t, we have a minus 3c2 minus 2c1. This is going to go in for y prime. Our original is going to go in for y. We need y double prime. So it's just going to be more derivatives. Take the derivative of the first times the second. Plus the first times the derivative of the second. The cosine's negative sign, so -2 derivative of sine is cosine. This is going to require some cleanup as well. And I recommend the same cleanup program that we had before. Factor out the e to the -3t. Figure out what your coefficient, I have two signs. Figure out what your coefficient of the cosine of 2t is going to be. It's going to be like C1, C2. Same thing for sines. Because algebra. So I'm going to factor out an e to the -3t. I'm going to think, what's my coefficient of cosine? For cosine, I've got this cosine of 2t, which is going to be 9c1 minus 6c2 cosine of 2t, and then minus 4c1 minus 4c1 minus 6c2 for this cosine of 2t. So in total, I have 5c1 minus 12c2 times the cosine of 2t. Plus. For the sine of 2t, I've got this one, which has to get multiplied by -3. So that's going to be 6c1 plus 9c2. And then this one down here, 6c1 minus 4c2. So that looks like it's going to be what? 12c1 plus 5c2 on the sine. Now all we have to do is take the y double prime, y prime, and y, stick it back into our original differential equation, and make sure everything fits in. I don't know what made me feel like doing this algebra. I think just to demonstrate how why we want to simplify things. Because really, all the derivatives are going to have this e to the -3t out in front, and then some combination of cosine of 2t and sine of 2t. And even though it keeps coming up in these two big terms, we need to clean those up to get that same format. All that's going to happen is these coefficients of cosine and sine are going to change up as we take more derivatives. Also, I said you should never just trust everybody, anybody in a position of authority. And so that means if you find yourself in the position of authority, make sure you back up your ruling with a proof every now and then to maintain trust. If all this sounds too manipulative for you, this is human communication that we're working on, and that's always just very manipulative. Any questions? Comments? Snide remarks? Also remember, it's people that are in a position of authority that need to be questioned. Notice that if you all send me an email and said, oh, Leach, I'm so sick, I don't ask for a note, I'm the one in the position of authority, I just believe you. That's because I would like to treat you like an adult with some respect. And just work on the operating theory that if you feel like you need to lie to me because you're not going to be in class, then that's okay. I feel like I failed at that point. That you can't just send me an email. It's like, oh, Leach, I'm not going to be in class today. You know what I mean? It could just be that you wake up and like, oh, no, I don't want to hear it. I don't want the first thing that I hear in the morning to be Leach, just bleh, 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 about math for an hour. So you just send me an email. Oh, Leach, I can't come to class. There's something wrong with my eyes. I just don't see myself going to class today. And that's, you get like 10 of them. You get 10 sick days. That's crazy. It's un-American, I tell you, to give you 10 sick days for this class when there are only 17 weeks of class. Un-American. Well, that's too many sick days. How are we going to prepare them for their future slave labor if we don't take away all their sick days and make them bring doctor's notes like they're children? Nah, man. They get to make their own decisions. You know what I mean? You gotta be careful. There's a lot of crazy teachers out there that don't think they're authoritarian, but they are 100% authoritarian. They just don't want to think they're authoritarian because it makes them look bad. But that's only because they're authoritarians, and that's a bad look. You know what I mean? What are we talking about? Oh, yes. The other important thing to remember, just from a math standpoint, is that when you're solving differential equations, you are solving an equation. That means at the end of the process, there's never any question whether you're right or wrong. You check your answer, and you'll know if you're right or wrong. When I see a math book that has solving equations in it, differential or otherwise, and they put answers to the odd numbered questions in the back, I think that's a fundamental failing on the part of the math book. You don't need to check your odd numbered answers in the back. It's an equation. Check your answer in the equation, and you'll know if you're right or wrong. That make sense? Honestly, I think the last word spoken before the odd answers were printed in the back of the book. I know that the last word that was said before the decision to print the odd answers in the back of the book was fine. Because all I could see is it's just a parent the whole time, a kid and a parent. Hey, can we have the answers in the back of the book just so we can check? We have the answers. 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 And then finally, I was like, "Oh, fine." And then the next edition came out. It had the answers in the back of the book. What about the even ones? Quiet, dude. We're compromising. What are we talking about? Oh, yes. So, three things can happen when you're solving second order differential equations. We can get distinct real zeros, repeated real zeros, or complex conjugate zeros. Three different ways to build your general solution. Note that our three general solutions all have two constants. So if we want to solve for those, we would need two pieces of information to figure out what they are. Any questions? Comments? Snide remark? It's too late in the semester for that kind of stuff. There's only one question. Can I just have an A? I'm like, oh no. Y'all don't have enough money to just buy a grade. I can tell. If you had enough money to just buy a grade, you wouldn't be here, you'd be at Harvard, you know? All right, Harvard, next time I'll pick on Yale. Is that okay? All right, that's going to do it for today. I will see y'all on tomorrow. Have a good day, and thanks for playing.